Hello everybody, welcome to the ETABS and SAFE course. Now in this lecture we want to define the lateral load on the building. Lateral load are earthquake load or wind load. If we go to the AutoCAD file, we show that lateral load or seismic load are a lateral load. This lateral load create an internal force on the building, maximum and the lower story of the building. This lateral load create or generate a displacement of the building. This displacement has a limit according to the earthquake code using and the calculation and analysis. Our building must not exceed this limit of story displacement. So also to make our building resisting against this lateral load, wind or seismic load, we must use a system to resist this load. We can use many systems to resist earthquake load or wind load. One of the most used systems are shear walls system. Shear wall system consists of using a concrete reinforcement walls and the building to resist this lateral load. So there are many other systems we will define then and this lecture. On our project we use shear wall system as we show. So we return to the presentation. We show that and slide 23 use and this project the code UBC 97 code. This code is for lateral load design. Lateral load design earthquake we have two methods. The first method called static method and the second called dynamic. When analyzing a structure against earthquake, we have two cases: static case and dynamic case. When we are in the static case and when we are in dynamic case. If we go on the next slide, we show that we have regular or irregular building. Regular building means that all the plans of the project is the same. That means that story 1 is the same plan of story 2. Story 2 is the same plan of story 3, and then so a building is regular when all these plans and all stories is the same plans, and the rigidity of all plans is the same. That means that we story 1 we have the same section of column, the same section of shear wall. We don't have a rigid plan, more rigidity than the other. And our project, all the plans are the same, and we have the same section of shear wall. So the rigidity of each story is the same for the. So if the building is regular and the height of the building is below 73 meter, we are in the static case. If the building is regular and above and its height above 73 meter, we are in the dynamic case. If the building is irregular building and we are below the 21 meter, we are in the static case. If the building is irregular building and we are above 21 meter, we are in the dynamic case. If the building is irregular building and the number of story equal 5 and above, we are in the dynamic case. And the code, the UBC code said that if the eccentricity between the center of mass and center of rigidity above 20%, we are in the dynamic case. What means this line? We go to the AutoCAD and we show this plan. This center and color is represent the center of mass. The center of mass is related to the shape of the building and the centroid of the shape of the plan. So if we have a rectangular plan, the center of mass is the middle of this plan. Center of rigidity represent the rigidity of the shear wall or the system used for resisting the earthquake. That's mean if we have a shear wall here, the center of rigidity will be in this place, is near the shear wall. If we have a shear wall here, the center of rigidity will go to here, will move right. And if we have the shear walls here, the center of rigidity will move up to here, will move up. So the center of rigidity is related to the position of shear wall. More when the shear wall are symmetrical and the plane, more the center of rigidity is close to the center of mass. The percentage, this percentage 20%, how we calculate the percentage between center of mass and center of rigidity? We measure the x distance between center of mass and center of rigidity, and we divide it by the length of the plane and the x direction, and we multiply the result by 100. We get the percentage and the x direction. The same thing for and the y direction. So if any of this length, any of this percentage and the y and the y direction or x direction is above 20%, we are in the dynamic case. Now, and also the code said that the minimum percentage between the center of mass and center of rigidity equal to 5%. Even then, the center of mass and the center of rigidity are close together. The code for safety take into consideration a 5% between these two center. So we must check our project if it is a regular or irregular building. Our project, we show that all the plans of this structure are the same plans. So we have a regular building. The height of the building, our project is equal to 49 meters. So we are and static, we are with regular building below 73 meter. So we are in the static case. We must check the percentage between center of mass, center of rigidity, and we know that ETABS calculate automatically this eccentricity, this percentage of eccentricity. We will show it and check it again after and the next lecture. Now we will assume that our building is a regular building below 73 meter and we are in the static case. But to learn how we define the dynamic, we will also define the dynamic load. Even then we work with regular building. So we have a regular building, but to learn how to define the dynamic load, we will assume that we are in the case and the dynamic case. So also we must know that if we are in the dynamic case, we must define static case. Why if we are in the dynamic case we must define static case? Because we will compare the dynamic case with static case. If the dynamic case is below the static case, we want to increase the dynamic case to be minimum equal to the static case. So if we are in the dynamic case, we will show pair the base shear and the dynamic case with the base shear and the static case to make sure that the base shear and dynamic case equal minimum the base shear and static case. So if we are in dynamic case, we must define static case. Now we will go to the ETABS software and we go to define load pattern. We want to begin to define the static loads. If we want to define the static load, we have to define 4 loads. The first load, the first earthquake static load, we name it VXP. That means that this is a positive earthquake load and the X direction. So we name it VXP. The type of this load we change to seismic. It is a seismic load. We choose here the code using and calculation. We use the UBC 97 and we press here add the new load. We want to remind that dead load and live load are a standard load that ETABS define it automatically. And also we must know that the earthquake load, when define earthquake load, the ETABS automatically put here on the building and modeling this load automatically on the building and on the structure. So we must know that when we define the earthquake load or the wind load, ETABS automatically modeling this load on the structure. We don't need to like dead load and live load to put this load. Just we must define this load. When defined the first load, we go to modify it. So we will continue to define the 3 load. The second load is VXN. That's mean earthquake load, negative earthquake load, and the X direction. This type seismic and we code using UBC 97. We press add a new load. The third load the third load is VYP. That's mean positive earthquake load and Y direction, type seismic and with code UBC 97. The last load, its name is VYN, negative earthquake load and Y direction. Press add a new load. We return to the PowerPoint and we want to define and know how ETABS calculate and what are the coefficients must define it to calculate. Tell ETABS. Now we return to the PowerPoint to know what is the formula of the static method and what are the coefficients must be modified and the ETABS to calculate the earthquake load. First of all, the equation using for calculation the base shear and static load is V. That V means the base shear load, base shear equal to CV, numerical coefficient dependent of the soil condition at the site and the seismicity of the region, times I is the seismic importance factor, over R times T. We will talk about each coefficient in the next slide. Times the seismic that must know that we have a maximum base shear and minimum base shear. ETABS automatically take into consideration these 2 loads and calculate them automatically to make sure that we are between these loads. We go to the next slide. First of all, we want to know what are the location of our structure to now and which zone we are. For example, our project is located on Lebanon. Lebanon is located between the zone 2B and 3. So we are in the middle of these 2 zones. So first of all, and what zone we are? So we are in the middle of these 2 zones because our structure is located in Lebanon. We go to the next slide. This slide defines the seismic importance factor. We must know what are the type of our structure. If it is a residential building, the importance factor equal 1. If it is an hospital or a government building, the importance factor equal 1.5. This is the table that define all cases may face with us. We go to the next slide. We define the time period. The time period is the time of the one oscillation, one earthquake load. When we have a seismic, the building go with an oscillation. This oscillation have a time period. ETABS automatically calculate this period, but we can calculate it manually. CT is a coefficient dependent on the system using to resist the earthquake. Usually we use 0.02 for all other building reinforcing concrete building, so we use 0.03 is the most using coefficient CT. HN is the height of the building. We go to the next slide. Here the code said that approximately if we have 10 story, approximately TA equals 0.1 times n. N is the number of story. For example, if we have 10 story, approximate TA equal to 0.1 times 10, so equal to 1 second. We go to the next slide. Here the code define the system that we can use to resist earthquake. When we use the coefficient R is related to the system used. For example, we can use pier wall system with concrete or steel or any types of material. The bearing wall system, that means we don't have a column and the project. We are only have walls that bearing the lateral load and gravity loads. The building frame system is the system that the building frame system means shear wall system. We can use shear wall system with concrete shear wall system. Building frame system is a system that consists of columns and shear walls. And this project we use building frame system with concrete shear wall. So if we show here, we have shear wall, concrete shear wall, so R equal to 5.5. For this thing we take R equal to 5.5. We go to the next slide and we have other system, moment resisting frame. That means we don't have a shear wall resist the earthquake. Dual system means that we make the shear wall and column and beams, and which are the frame of the structure. So the frame and the shear wall system are responsible to resist the earthquake load. Now on this project we use building frame system, concrete shear wall system, so R equal to 5.5. The seismic dead load W is the seismic dead load included the total dead load of the structure including the total weight of permanent equipment. So W is the dead load of the structure. We can also include 25% of the live load if we have storage and warehouse occupations. The weight of snow, and if we have snow, we can use 75% of this load. Now here in this project we will not include the live load and the snow because we don't have storage or warehouse or snow load. So W and our project equal to dead load only. We go to the next slide. To define the earthquake load, we must know the soil profile type of our project. So we must to know the soil profile type, we need to know how much equal the bearing capacity of soil. If we go to the first slides, we show that we have a bearing capacity of soil equal to 3 kg per centimeter square. So 3 kg per centimeter square equals 3000 kilopascal. So we are, and this soil profile, the soil profile name is very dense soil and soft rock, and our project. So we are and the SC soil profile. SASB is we have a rock soil. So and this project the soil profile is SC. Now the last slide is consists to calculate the CA coefficient and CV coefficient. CV coefficient, we need CV coefficient to define it and to calculate. CV coefficient is the equation of the calculation and base shear, and CA coefficient is included in the equation of Vmax and Vmin. So we must calculate this coefficient and define them and into the ETABS software. We want to remind that we are in this zone between 2B and 3 because our structure is located in Lebanon. So we have a CSC soil profile type, and we are between these two zones. So CA here of our project equal to 0.24 plus 0.33. We do an interpolation between these two zones. So CA and this project equal to 0.285. Also for CV equal to 0.32 plus 0.45 times 0.5. We do this interpolation, so CV equal to 0.385. Now we return to the ETABS and we must to modify each load. We go to modify the first static load. We press here modify lateral load. First of all, we have an eccentricity, as we said before, minimum eccentricity equal to 5%. So 0.05 represent this 5% of eccentricity between center of mass and center of rigidity, and we must uncheck the x direction and x minus eccentricity, x, y, and all the y direction, because we are in the positive direction plus eccentricity because VXP. Okay, for CT we said before that equal to 0.02. Story range, the earthquake began from base to the last story. As we said before, for R we have R equal to 5.5. The importance factor of our project, we have a residential building, so I equal 1. Now we want to define CV and CA and CV. Okay, we can directly use the soil profile and the zone, but Lebanon, the Z of Lebanon, it's not included here, so we can define manually CA and CV. We have said before that we have CA equal to 0.285 and CV equal to 385. So now we terminate from modify this load, the first load. So we press OK. We go to the next load, static load. We press here modify. The same thing, we check this direction and eccentricity, x minus direction. We put here CT equal to 0.02 and R equal 5.5, I equal 1, and here we put we will do the same work with the other load. So now we have terminated from defining and modified the static earthquake load, and we want to remind that we are in the case and the static case. But to learn how to define the dynamic case, we will define it in the next lecture, and we will compare the two cases, dynamic and static, together to make sure that the dynamic load is equal minimum to the static load. Okay, so we press here OK, and the ETABS automatically define the earthquake load and modeling them on the structure. And then thank you for listening. We will continue